Thanks for coming. Today we will deal with another installment of my introduction to sets. Today we deal with the representation of sets, cardinality of sets, and types of sets. Those are the three topics we're going to cover in this video. Before I continue, please subscribe to my channel, like and share this video, leave comments or questions under this video. I will answer your questions or comments as soon as I can. Alright, so let's kick it out. You see the map there? The map there represents the map of the United States. The one map at the middle is the map of the United States. And then the map on the left is a section of the map on the middle. And then the map on the right hand side is a section of the map, in the middle. Notice that the map on the left is called, it consists of 3 states. And it's called the West Coast of the United States, right? And then the map on the right hand side consists of, I think, about 11 states. And it's called the Northeast of the United States. So I'm going to use the map to demonstrate something for you. That way you understand what we're doing, okay? But mainly I'm gonna use numbers. But when I start with the map, it will help you to get a little bit more understanding of what I'm doing. We define a set and introduce the elements of set. The elements of sets determine the membership into a set, right? Now, under representation of a set, I would describe I will explain 3 methods of representing a set. Let's say you have a set. You see the map on the left is a map of 3 states, right? And the map on the right is a map of 11 states. So those 2 maps cut out of the main map of the United States can be considered a set. They are a set. The one on the left is a set of 3 states. The one on the right is a set of 11 states. And then the main map is a set of 50 states of the United States, right? So let me show you the three methods used to represent a set. All right, there are 3 methods applied to describe a set of elements, right? The first method is called the description method. The second method is called the listing method. And the third method is called the set builder method. I'm going to explain each method and then use the example. Okay. The first method is just a description of the set. Okay, description. Okay, so see the three states on the left side of the big map, and those 3 states are collectively called the West Coast of the United States, right? Okay, you can describe that set like this. You can say it is a set of West Coastal states, right, of the USA, okay, whatever, USA. Okay, so we can call that set, we'll call it set A, right? We can call it set A. Set A is a set of West Coastal states of the United States, right? Okay, there is another way to describe the same set. We can use method 2. Method 2 is called listing. You list the elements of the set, right? You can say set A is equals to, you list the elements of this set. Washington, you write Washington, comma, Oregon, comma, and then you write California. So basically you list the elements of the set and then you enclose them in that kind of bracket you're looking at there. That's what they call the listing method, right? I mean, you can abbreviate the elements. You can call this one W, little w, call this one little o, call this one little c, if you want to. But for now, it's good to write the whole thing out. That way you understand what I'm saying. Now, number three method of building a set, representing a set. Basically, you use it's called set. The third method is called set builder method, right? Set builder. It's called set builder. What that means is, you use a variable, right? Let me write down. You use a variable. Use a variable. In mathematics, they usually use x, y. So you use a variable. You also use the brackets, right? You say A is equals to x. X is a variable. Use the variable x. X is such that x is a state in the west coast of the USA, right? So you close it with the bracket. So you say x is just that. X is a state in the west coast of the United States, right? The way you read that, you see, you know what is bracket, but you see, you choose a variable. You say the variable is, this thing is read such that. Then you describe what that x stands for. In this case, x stands for a state in the west coast of the United States. All right. Now let me show you the third method is just an abstraction. An abstraction mathematicians use, you see. You remember yesterday we talked about the elements, the membership, the members of a set, right? So basically, you can say that Washington is a member of set A, right? That's what that means. You can say Oregon is a member of set A. And you can say California is a member or belongs to, right? The same thing, belongs to set A, right? But you see, you cannot say this. Well, I guess you can say this. Say it like this. Texas does not belong to set A, right? And then you can say Iowa does not belong to set A. You can say in any other state you can think of. You can say Indiana, right? Indiana does not belong to set A. See? So make sure you understand that this method is just abstraction. Mathematicians try to, put things in abstract way. That way it's compact, So but sometimes it confuses some people, So if you look at what that says, if you look at what this says right here and what that says right here, look at it carefully. They're all saying the same thing. Basically, they're all saying the same thing. Right. The previous example can also be written like this in still more compact, abstract form. You can say A is equals to W O C, and then you say W is an element of A, O is an element of A, C is an element of A, P is not an element of A. Where I mean by P, I mean Pennsylvania. Of course, W stands for Washington, O stands for Oregon, C stands for California, right? So I want you to get that. Try to understand that. If you understand that everything else is a piece of cake, well, I don't want to, insult anybody. Now, listen to this. Do you remember in the past we worked with a set of whole numbers? So here are the a bunch of sets, regularly used in mathematics, right? You can say useful, it doesn't matter, useful sets in math, right? You can say whatever, or you can say sets used often, right, in math. It doesn't matter what you want to call it. Number one, you remember the set of natural numbers. That's how they write it there. The set of natural numbers. This is the set of natural numbers. It's a set, natural numbers, right? And it's represented like this: 1, 2, 3, to infinity. So the set of natural numbers usually a set of counting numbers, numbers you used to count. Okay, here's another set that is very common. That's the set we used last time when we were doing all that arithmetic. We first started using this set. It's called a set of whole numbers. Whole numbers, right? Set of whole numbers. It's the same thing as you just add 0 to a set of natural numbers. 0, 1, 2, 3, and then to infinity. Okay, it's the same thing. So right there. And then you have what they call set of integers, right? We talked about that before. This is example number 3. The set is being used by mathematicians regularly. A set of integers, usually represented by Z, the letter Z, is equals to, let me write it in word first. I describe it first and then I can write it in form of abstraction. It's called a set of integers. Okay? Set of integers is like this. Again, it's everything above, but you introduce negative sign. So, watch this. It says 0, right? 1, 2, 3, dot to infinity. But you introduce the negative numbers. -1, -2, right? -3 to infinity. You keep going to infinity. So basically that's the set of integers, right? And then remember the set of number 4 is the set of rational number. They call it set of rational numbers. It's represented by Q rational numbers. That's a set of rational numbers. Like I said before, they're not. Don't use the word rational the way you use it in when you multiply words. Rational only means they are ratio. They are ratios, right? They're not rational because they think or they don't think. No, that's not what that means. So they are represented like that. Because you know they are ratios, which means fractions. You say A over B, right? Such that, you see why mathematicians love abstraction, such that A and B are element of Z, which is they are integers. That's what all they're saying. A and B are integers, right? And B is never zero. See, that's a set right there. See, you see, I wrote it in abstract form, but see, you can write the same thing. You can write the same thing as A over B, where you say where A and B are integers, right? Integers. And B can never be zero because you don't want to divide by zero. See, that's the same thing they're saying up there. It just takes a while for you to just understand what they're saying. You gotta look at it over and over again until you understand. Like I said, mathematicians love to put stuff in abstract form. So, and then another set, the final set I want to introduce, you already know. Number 5 is a set of real numbers. They're represented by big letter R. A set of real numbers. Set of real numbers, right? Real numbers. Real numbers, right? Now, what does that mean? It doesn't mean that they read everything else is false. That's not what that means. It doesn't mean that these numbers, you see, the same thing like this. Everything we describe above, right? You got, let me see, dot, minus 3, minus 2, minus negative 1, sorry. I keep saying minus. Then 0, 1, 2, 3, to infinity, right? But notice though, they also include things like everything on the number line. They include everything on the Cartesian coordinate system. 0 here, everything there they included. So which means they include over here you have let me see, you have negative half over here somewhere here. You have you could have what do you call that? You could have you remember something like you have a half over here. Half over here. Over here you got 2.5. So they contain everybody. Those are fractions. It contains fractions too, right? So it contains everything above, everything listed above. That's all. That's all that is saying. Our next topic is the cardinality of sets. Cardinality is defined as right here, defined as the total number of elements in a set. Simple. Sometimes it's also called a cardinal number. And then note this, note here, if a set has an infinite number of members, then the cardinality will be equals to that in there, which is infinity, right? And then here is the symbol of cardinality. The symbol is 2 lines. You put the set into 2 lines. It looks like the symbol of absolute value, but it's the symbol they use. Let me give you an example. Remember our set? Remember our set at the beginning? That's why I started with that set. You remember? We said that A is equals to W 0 O C. This is the states in the western coast of the United States, Washington, Oregon, and California, right? What is the cardinality of that set? The cardinality is like that. It's just 3. Because why? It has 3 elements. Right? It has 3 elements. The 3 elements in there, are listed there. We listed it before. Okay, what of the states in the states in the northeast? Let's say set B is equals to the northeastern states. Northeastern states of the United States, right? Alright? It's a set of the northeastern states of the United States. Of course, we know that's what that set will look like. The image I showed you before, that set will contain, let me see, CT. CT stands for Connecticut. What is this? ME stands for, oh, don't tell me I get that wrong. I think it stands for men. ME stands for men. That thing stands for men. That's ME, right? Okay, and then NH, that stands for New Hampshire, right? And then, let's see, NJ stands for New Jersey, right? And then NY, of course, it stands for New York. I know that one by heart. Stands for New York. And then PA stands for Pennsylvania. And then RI, I know that one too, Rhode Island, right? You keep going until you list all the states. VT is, what's that again? It's a Vermont, yes. And then DE is what? Is Delaware. And the last one is MD. MD is Maryland. So you close that with brackets. So if somebody will say, see how many states are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're missing one. Okay, what we were missing was Massachusetts. I put it in there. So we have Connecticut. ME stands for men. And then NH, New Hampshire, NJ, New Jersey, NY, New York, PA, Pennsylvania, RI, Rhode Island, VT, Vermont, DE is Delaware, MD is Maryland, and MA is Massachusetts. You know, how am I going to forget Massachusetts? You know, I can't forget that. So how many states are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So since you have 11 states, if you're looking for cardinality, you write it like that. Cardinality is just 11. That's all. That's what that says, man. You know, so we'll move on. Let me see what I have for you. We'll move on to another example. Let's say I have this example. I say, let W be a set. Be a set consisting. You see something like this in exam somewhere. Consisting of all the, I'm sorry, my pen is getting dry or something. Consisting of all the letters in the word. In the word Washington. I put it in bracket, in the word Washington. That's why I want to use this example. Let W be a set consisting of all the letters in the word Washington, right? First, let's form the set. So we said W is equals to what? Now pay attention. It consists of W, A, S, H, I, N, G, T, O. We don't write N again because you remember that the N, there's already N here. You don't write it again because a set contains elements that are distinct. In other words, they are different. You can't repeat. You can't repeat 1 or 2. You can't write 2 twice. You can't write N twice, right? So that's what that means. They are different. So now, having written that, suppose they say find the cardinality of W. You just go like that. You count off the elements. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 9 right there. Okay, so I'll give you another example. Uh, see this example here. Suppose you're given this. This is a set of natural numbers. You remember? We just talked about that a few minutes ago. 3 and then down to infinity. What is the cardinal number? Remember, I put that in definition of a cardinal number. It's just that because the set goes to infinity. So the cardinal number is that and there. So let me give you one more example and then we'll move on. What of this set here? Suppose you're given this set T is this set X such that X is an element of the N, which is natural numbers, right? And another condition is that X is less than 6. So follow what they're saying there. This is natural numbers, which is 1 to the accounting number to infinity, right? That's what that means. So X is an element of that, X is less than 6. All that means is if you draw your Cartesian coordinate, right, you have 1, 2, 3, 4, 5, 6. If you get confused, draw that. They say X is less than 6. X is not included. So X is over here. See? Going that way. And then it ends in 1 because after 1 there's nothing else in natural numbers. So basically T is the same thing as 1, 2, 3, 4, 5. That's it. 6 is not included because it says less than 6. If it says less than 7, then you put 6 will be included. What is the cardinality of T? You do like that right there. Just 5 elements. That's what that's saying. I noticed I made a mistake there. I left the word arithmetic out there, but I have since cleaned it. Now let's deal with new topic. Our new topic is set of different types of set, right? Different types of sets they have up there. The first set we're dealing with is empty set. Empty set just means what it says is empty. It has no element in it, right? There's no element in it. Another name for empty set is null set or void set. It's just a set that contains no element. That's it. They use the symbols that this Greek symbol here look like a big 0 with cross it out like that, or you can just write bracket. That's a bracket and put nothing in it. So that's the symbol they use for that. Now let's look at this set. It says look at the example. A is equals to S such that X is an element of N and X is greater than 10 and then X is less than 4. Okay, see, I drew the Cartesian coordinate there. See what it says, X is greater than 10. If you look at that, there 10, it means X starts here. It doesn't include 10, but it goes that way. So after 10. So basically it starts, since your natural number, it starts at 11. No, it doesn't start at 10, it starts at 11. Okay, that's what that's saying. But look at the second condition. It then says X is less than 4. Which means it's here. It starts at there, but it's actually starts at 3 and go that way, which is impossible. X cannot be less than 4 and greater than 10. That's impossible. So that means this set is an empty set. You write it like that. It's an empty set. Okay. Now suppose you want to find the cardinality of an empty set. The cardinality of an empty set is 0 because there's nothing there. It doesn't have any element. The number of elements it has is 0. Now we'll move on. We'll deal with what they call finite set. Yeah, finite set. Right? And I want to group it with infinite set. Infinite set. Those are two types of sets, but the opposite of each other. Finite set basically, it basically means Finite set means a set that contains finite number of elements. So in other words, the elements are finite. It doesn't go to infinity. Right? That's what that's saying. Contains finite, right, number of elements. I will give you an example in a minute. Infinite set, on the other hand, infinite set contains, is the opposite of finite sets, contains infinite number. Infinite number, you guys say infinite. Infinite number of elements, right? That's what Americans say. Infinite number of elements. So I'll give you example. Look over here. A is equals to x such that x, this is small x now, not a big x is a natural number. A natural number. I just want to write a natural number, right? X is a natural number, and x is a natural. That's it. So what does that mean? Okay, look at another set. B is equals to x such that x is still a natural number and x is less than 10. Okay, look at those two sets, right? A is a set consisting of natural number. That means A is 1, 2, 3 to infinity. It's an infinite set, sorry. A is an infinite set. It's an infinite set. But B is finite because B is x is natural number x less than 10. So that means B is the same thing as 1, 2, 3, 4, 5, 6, 7, 8, 9. It doesn't include the 10. So this is B is a finite set. This is a finite, because the numbers they're not going to infinity. This is a finite set, okay? That's what that means. All right, see, this is one more example here. This is the set U stands for X. X is a state of the United States. Of course, U is finite because U contains 50 states, right? So I just want to, give you that example. That way it helps you to understand the concept. We'll move on to another type of set called singleton set. Singleton set, the name gives it away. It's a set that contains only one element. Okay, it contains only one element. That's all that is saying. I'll give you an example of a singleton set. Example is, let A be equals to this set that contains one element called Texas. It contains Texas. So it's a singleton. It's a singleton, right? Because it contains only one element, right? Okay. So let's give you another example. Let this set here, let this set A be this is x such that x is an element of natural numbers, right? That's how you write that. And x is less than 2. Of course, if we draw the Cartesian coordinate, right, this is 0, this is 1, this is 2. If it's less than 2, it means it starts here, and then it doesn't go to 0. It's only one element. So that means A is equals to a set with only one in it. So that's a singleton, right? A is a singleton. So basically, they can define a set, but if you read the condition very carefully, the condition leads you to conclude that the set contains only one element. That's all that is saying. Okay, so we'll move out to another type of set called it's called subset. Subset is another type of set. Subset basically means it's a set. See, it's a set that is a part. It's a part of another set. A part of another set. Again, each name gives it away. So this means there are two sets. There are two sets, right? A and B. And then it says A is an it's represented like A is a subset of B, like that. Whenever you talk about subset, there are gonna be two sets, right? This is the symbol, right? Symbol. That's how you represent that symbol. You know, symbol of that. That's how you represent that. Okay. Okay, so let me give you an example. Example will help you understand. Let's say we have this set, call it J. J consists of all the states, right? All the states in USA. That's J. And then it says B is equals to, it's the same thing as all the states in West Coast. In West Coast, right? Okay, so that's B. So notice something though. Notice that B is a subset of J, because all the states in the western coast of the United States, right? All the states in the western coast of the United States are also in the bigger set J, which is the state of all the states in United States. So that's what I want you to take away from that. You know, so let me give you another example. I'll give you another example. Let a set T be equals to it just contains a state called Texas, right? Again, notice that T is a subset of J. You see that, right? I can use numbers to show you what is there. How do you demonstrate this idea of subset? Let's have this set here. A consists of 2, 4, 6, right? And the 7. Now notice this. Notice that A is a subset of the natural numbers, because remember the natural numbers is a set consists of 1 to infinity. Remember that? So A is a subset of N. Okay, so somebody can write a set and then ask you to, write the subset of that set, right? Suppose I write this here. Suppose I write this set T equals to 2, 4, and 6. It contains 3 elements, right? I say, what are the subsets of A? Right? List all the subsets of T. So how do you proceed? Then check this out. There are 2 things I want you to understand. 2 observations. 1, every set is a subset of itself. Remember that. So every set is a subset of itself. The way set is defined, yes, every set contains itself. And then second observation, the empty set. The empty set is a subset of every set. All right, think about that, because empty set contains no element, so it's a subset of every set, right? So if to solve that problem, list all the elements in T. So if you can do it any way you want. You can say we know that T contains empty set. You put empty set. We know that C contains itself. We can write that set itself. And then we'll start listing out the elements. T contains 2. T contains 4. Right? T contains 6. Now we're not done. T contains 2, 4. That's a set in a subset of T. T also contains, 2, 6. All right. So how many sets are there? 1, 2, 3, 4, 5, 6, 7. One. There gotta be one more. Actually, it's this one here. It's 4, 6. It has to be 1, 2, 3, 4, 5, 6, 7, 8. It has to be 8. 8 subsets. How do I know that? Well, there is a remark here for you. There's a remark that will help you here. Just give me a minute. Let me get it for you. Here is the remark that will guide you when you're looking for number of subsets in a set. It goes like this. If a set contains n elements, okay, if it contains n members, right? Then it must contain 2 raised to power n subsets, right? In other words, a set with any element contains 2 raised to power n subsets. So if you see what we did here, this set T contains 3 elements, right? So it must have 2 raised to power 3, which is 2 times 2 times 2, which is what? 4 times 2, which is 8. It must have 8 subsets. That's what that remark is saying. So if you count it 1, 2, 3, 4, 5, 6, 7, 8. So that's like a guide to guide you when you're looking for a subset. That way you know how many you should get before you quit. Okay, so here is another type of set for you. It's called proper subset. Okay, let P and A be 2 sets, right? Then P is regarded as a proper subset of set A, right? If this means there exists, right? There exists at least one member of A that is not a member of P. Alright, I'm going to explain what that means, a member of P. Basically, that means that it means that A has more elements than P, right? Another way to see it, the cardinality of A must be greater than cardinality of P. That's what that means. See, proper subset, means A has at least one element that is not contained in P. So A has more elements than P. So it must have more cardinality than P, because cardinality just means the number of elements in a set, right? What is the symbol? The symbol for proper subset is this. Yeah, don't get it confused with the subset. See, you just have to, just read this over and over again until you have it. Subset, is this. Subset is this symbol, right? Proper subset means that is that symbol you're looking there. So based on that, the description we're giving up there, basically say P is a subset of A. That's how you write it, right? So let's do example. We'll do example here. Let's do example. Okay. Let's see. Let P equals to all the states in the west coast. The west coast of USA, okay? Alright. Okay, and then let A equals to all the states in USA, in old USA. Okay, so if you have that, then you can see that A contains more elements than P, right? Because A contains 50 states. P contains only 3 states like we described before. So then that means that P is a proper subset of A, because A has more elements, right? A has 50 elements, P has 3 elements. As long as A has 1 element more than P, then P is a proper subset of A. That's all that is saying, don't get confused, sorry, it's a lot of stuff to cover today. I want to, cover all this stuff today. Let T be a set consisting of 1, 2, 3, 4 as elements, right? And then remember our usual N set of natural numbers, which is, it starts with 1, 2, 3, 4, and it keeps going to infinity. Remember that? And then notice that T is a subset of N, because T is inside N. T has less element than N, right? Okay, let's give you another definition. What of this one called superset? Superset. Basically, it derives from a proper subset. So above, it will say that P is a proper subset of A, right? This says that if P is a proper subset of A, right? Then A is also called, is regarded as, A is called a superset, a superset of P. So basically those two go together. Proper subset and superset goes together. If you understand one, you understand another one. And the symbol for this is this way. You know, they say A like that is superset of P like that. You see, this is an inversion of proper subset. Remember? Let me see. It's a little bit confusing. Actually, they added more stuff to it. It's just a little confusing. But it's okay. Just read that, you know. Let me give you an example. The set we described before, up there, you know, we described this set T is equals to 1, 2, 3, 4, right? And then N is a set of natural numbers. Go from 1, 2, 3, 4 to infinity, right? Keep going. Then according to the definition of a superset, N is a superset of T. Like that, you write it like that, because N contains a lot more elements than T. That's all that is saying. You know, hopefully, you know, you're not too overwhelmed. All right. Here's another type of set. It's called Powerset. Powerset basically says that if you have a set A, right? Let A be a set. Okay. Then it's saying the power set of A, power set of A consists of all the subsets. It consists, I'm sorry, I gotta get my grammar correct. The power set of A consists of all the subsets. Subsets of A, right? Including, of course, it should include, including the empty set, including the empty set. All right, that's all that is saying, including the empty set. Of course, you will include it, you know. And then the symbol is written like this. The symbol is like this. The power set of A is written like this. Power set. It looks like probability. I don't know how many of you know have done with probability. It looks like probability of A. But anyway, that's power set of A. Okay, so let me give you an example. Let's A be equals to this set 1 consisting of 2 elements, right? Then you have empty sets. You have A itself, which is 1, 2, and then you have 1. A set consisting of 1. You have a set consisting of 2, right? So that's all the sets inclusive, because you remember that our formula 2n. This thing has 2 elements, so 2 over 2 is equals to 4. It must have 4 elements right there. So these are, it's exhaustive element of PA, right? And then we'll say PA, the power set. The power set is a set, or it's a set, it's not a number. It's a set of sets. So you write it like this. You write it like this. That's why it's called power set. It's a powerhouse. See, it's a set of sets. So you have to write it like that. They say the power set of an empty set is also an empty set. Well, I guess that makes sense. But anyway, that's how you do that. That's power set right there. There's another set I want to cover, another type of set called the universal set. It's called You hear about that you read about that, hear about that in books. Sorry, I made a mistake there. It's called universal set. So what does that mean? Universal set, usually they're represented by capital U. Universal set is just a set. Let's say you're solving a problem, right? Every problem it comes under stipulated condition. What I call the domain of discourse, what you're discussing, right? So universal set is just it's a set. It's a set in a particular problem situation, right? That's how I understand it. In a particular problem situation, okay, such that all other sets in that problem, right? Particular problem you're solving, all other sets in that problem are subsets. I will give you an example. A subset of subset of the universal set. It's kind of tautological, right? So this basically is saying, what he's saying is the universal set contains all other sets associated with that particular problem. That's all. It contains them as subset. All of them, all the other sets are subsets of it. That's all he's saying. And they, like I said, they're donated by you, universal set. Now, let me make this remark. Like I said, every problem has a particular domain of discourse. And that problem is also constrained by the definition of the problem, right? All right. So universal set does not necessarily mean a set of all objects in the world. No, that's not what that means. A lot of people confuse you with that. Universal set doesn't mean that. It's just a set that is a problem specific. It's contextual. Depends on it's unique to each problem. Each problem has a universal set. The universal set for one problem may not be the universal set for another problem. Let me say notes right here, right? Universal set does not mean a set of all objects in the world, in the universe, right? In the universe. That's not true. That's not what it means. It does not. So it's just problem specific. Every problem has what they call universe of discourse. You probably had the word universe of discourse, domain of discourse, right? I will give you an example. Example will help you. It will help you understand the definition. Definition is a little bit tortuous, but let me give you an example. Let's say A is a set consisting of W. Remember W, Washington? B is a set consisting of O, which is Oregon. And C is a state consisting of what? C, which is California. And D is a state consisting of Washington and Oregon. So see, the universal set in this case, see, all these are particular sets, right? The universal set, which is you, is the same thing as that set we started with. Washington, Oregon, and C, which is California. This is the universal because all these are subsets, right, in this set. That's what that definition is saying. So this set is the universal set of all these A, B, C, D sets, right? You can even have another set called, well, it's okay, I don't want to confuse you. So that's how you read that, right? All those sets are the subsets of set U, the universal set. Let me give you another example. Something wrong with my pen. That's okay. I'll change the lead. Let's say this is a set right there. Okay. And then let's say this is another set right there, containing two elements. The first set contains two elements, right? Now notice that those are natural numbers. So then we can say those two sets are subsets of the natural set of natural numbers, which is what do you call that? 1, 2, 3 to infinity. So natural number is the universal set for them. Natural number is the universal set for set K and set J. So that's how you understand that, because sometimes you have to make stipulation. I will give you example. You have to make stipulation, that way people know what is the domain of your discourse, right? If you don't do that, then people will get confused or they arrive at the wrong conclusion. Let me give you an example. Suppose set A, we quote it to a guy called Socrates, right? Socrates. And then let's say set B contains a guy called Obama. You guys know Obama. And then set C is a set consisting of one person called Hillary, a woman called Hillary. It doesn't have to be Hillary Clinton, any Hillary. And then let's say set D consists of a woman called Monica, right? Okay, so notice the commonality of those four sets. So we can say their universal set is this set. It's a set of humans, because all those people there are human beings. Set of humans, right? So if you're having a discourse, all those if you're discussing something with this set, it comes under human, under that set right there. The same thing with that, the same thing with that, the same thing with that. So let me give you one more example. Remember this set of natural numbers 1, 2, 3, 4 to infinity, right? Look at this set here. 4, 6. And look at this set here, containing 10 and 11, right? Don't you see that N is the universal set of A and B, because both A and B, they all contain natural numbers. So you can discuss stuff. You can discuss A and B based on the fact that you know that they are natural numbers, right? Once you specify the natural number is the U, the universal set. Once you know that those A and B come from U, which is natural number, then somebody reading you will understand the context, under which you making whatever claims you're making. That's all that means, man. Basically, here is another type of set called equal sets, right? Two sets are equal when they contain the same elements and also contain the same number of elements. So there are two conditions. They are the same elements and the same number of elements. All right, so look at set A. It has 10, 20, 30. Set B, 20, 10, 30. So set B and set A is the same as, even though set B, the numbers are mixed up. But they contain the same elements, right? And they contain the same number of elements, which each of them contain 3 of them. And each of them contain the same elements. So then we say that A is equals to B. That's what that means. So let's do another set that it goes together with the equal set. It's called equivalent sets. So two sets are equivalent, right? Two sets are equivalent. When they contain the same number. This one has to do with number. The same number of elements. Okay? The same number of elements. And the elements are not necessarily the same elements, right? There can be different elements. They're not necessarily the same. Okay, so an example will help you. See, the equivalent set contain one condition of the equal set. Equal set has 2 conditions. Equivalent set has 1 condition. So let's explain it with an example. Let's K be the set like this. It contains T, J, S, right? And let L be the set 7, 8, 9. Okay, see, the two sets are equivalent. Usually the symbol of equivalent is this. The two sets are equivalent, written like this. K is equivalent to L. The symbol of equivalence. Symbol of equivalence is this here, that thing there. So it's written like that over there. So because they contain the same number of elements. K contains the 3 elements. L contains 3 elements. They don't have to be the same, right? They can be different. That's what that definition is saying, and they're all different there. Let's look at another example. Let's look at example here. This one says J is equals, is the same thing as contains 6, 9, 12. Okay. K contains A, B, C, and the T contains 12, 6, 9. Okay. And then there's some more. Z contains S, E, A, M. And then Y contains S, A, M, E. Okay, notice that those are the sets given now. So which one of them are equivalent and which are not? notice that, and which are equal. Notice that Z is equals to Y. Why? Because they contain the same element, but the same number of elements, and then the same element, they just jumbled around. Somebody jumbled them around, right? And then notice that J is also equals to T, because they contain the same number of elements, but it's all mixed up. See, it's all mixed up, but there's the same element and the same number. And then notice that K is equivalent to T, because they both contain the same number of elements, even though they're different. You see that? So that's how you deal with that. Okay, here is another type of set. It's called disjoint set. Disjoint set. Okay, so disjoint sets. Two sets are disjoint when they have no element in common, right? There is another type of set that let me just write it down. They go together. It goes together with disjoint sets. It's called overlapping set. Okay. Two sets are overlapping, right? Overlapping when they have at least one element. Okay, one element in common. You see, I think overlapping sets are the opposite of disjoint sets, right? Remember the example we did earlier? We're going to use the same example. You see that we had this example. Let me see. We had T equals to 12, 6, 9, right? And we had Z equals to, what is that? S, E, A, right? M. Notice that T and Z are disjoint. Why? They are disjoint sets because they have nothing in common. They have nothing in common. And then notice that let me see, K. Let me write K. K is right here. K is A, B, C. Notice that K and Z are overlapping because they have, at least they have A in common. At least one element there, A is in common, right? We can pinpoint one element they have in common. So we say K and Z are overlapping. They're overlapping sets. You see? Okay, I want to conclude with this example. Look at that example carefully. You see that image? Basically, the image contains all the sets of numbers we've been talking about since I started, when I started doing arithmetic. Okay? If you look carefully, you should know what they are, but I'm going to explain them to you anyway. First of all, I said that notice that N and W are overlapping. Notice that set W and Z are overlapping. They're overlapping, right? notice that sets Z and Q are overlapping. Notice that sets Q and R overlapping. You see that? They're all overlapping. But let me explain what they are. I will write them in full. That way you can see that they're overlapping. See, let me leave it like that. Notice that N is a set of counting numbers. You remember? Okay, to continue to infinity. And notice that W, the set W is a set of whole numbers. It includes zero. It includes zero. What I wrote above, 3 to infinity. Right? So they're overlapping because they have a bunch of stuff in common. Right? Notice that set Z is this. You remember I told you so set Z is integers, so it's it goes to infinity is both ways. -3, -2, -1, 0, 1, 2, 3, then it starts going to infinity. So it contains everything above. It contains 0, it contains 1, 2, 3 to infinity. So notice a set Q. That's what they call rational numbers. It's a set of rational numbers. It says such that A is divided by B, right? Actually, yes, A divided by B such that A, right? When A and B are the elements of Z, which is integers, right? And B can never be 0. You remember that? So basically, to understand this, you see, 1 is on this set, 1 is on this set, 1 is on this set, right? Notice that 1 over 1 is in set Q. Notice that 7 over 1 is in set Q. So set Q has a lot of things in common with set Z, with set W, with set N, right? Because you can derive some stuff in other sets from, you can derive everything in set Q from any of the sets above, right? Okay. And then the last one, set of real numbers, the same thing. Set of real number contains all the other sets. It contains what all the other sets contains, right? It's like this, let's see, 0, 0, dot, 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 right? -3, -2, -1, 0, 1, 2, 3, dot, 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 plus more. It has the fractions in there. Remember I told you it has, let me see, over here is 2.5. No, I'm sorry, 1.5. Sorry about that. Over here is 1.5, which is a fraction right here. And right here, you find other fractions like 0.5. I'm sorry, -0.5. So, set R contains everything above. You see, that's why I drew that 5 concentric circles. See how they contain each other. But anyway, I'm gonna leave it there, and then we'll continue from there next time, okay? Please subscribe to my channel, like and share this video, leave comments or questions under the video, and then thanks for coming. I'll see you next time.